All right, so this is 8.10. This is the image we're given. We're given the internal bending stress at point K. We have to find the internal bending moment and the bending stress at point H. So to start, we need to write down the equations that we're going to be using. The main one is the stress equation, which is this. All right. Yeah, so this is the applied moment. This term, y of p, is the distance from the centroid of the shape to whatever point you're referencing. And then this is the area moment of inertia for the entire shape. So the equations to calculate that boil down to, so this is I sub x is equal to the summation. And so since this is a composite shape just made up of two rectangles, this I just denotes how many shapes that you're summing together. So we have the summations, and then I sub I, we'll calculate this in a second, but then it's I sub I plus area d, this you have i's, and then d squared, and then this is that 1/12 bh cubed term that we've been using a lot. So then this just is essentially summation of 1/12 base times height cubed plus a d squared. And yeah, these should all have i's. So this is just each shape that we break it into. We'll use this equation to sum them all together to find that total Ix term, which we then plug in here. So then, what's that? And then we should do the table thing that we've been seeing a lot. So we break this shape into two different rectangles, and we'll say that this is where we're going to separate them. So this is going to be, we'll call this 1, and we'll call this 2. So then we'll make a table for the two different shapes. So we just have this long rectangle, that's going to be 1, and then this wide rectangle is going to be 2. So starting with this, we pretty much need 3 terms in this table so we can move on to the next equation. And that's going to be your area of the rectangle, the, let's see, y bar, which would be the centroid and the y on the y-axis. And then you'd need y bar times a. So you just need to calculate these. And we'd see, so this is 1 right here. We know the thickness is 0.25. So it would just be 0.25. And then since we cut this thickness off and we have this whole distance, it would be 2.5 minus 2.25 to get the length of this side angle. So it would be 2.5 minus 0.25, which is 2.25. So that times 2.25 equals 0.5625, I believe. So it'd be 0.5625. Okay, now calculating the area for this long shape, we have a thickness of 0.25 and the length of 2.25. So those are the same numbers, so it'd be 0.25 times 2.25 again, which also equals 0.5625. So y bar is just, since these are rectangles, we know that the centroids of each rectangle lies at the very center. And since it's symmetrical along the x-axis, we only have to worry about the y positioning. So for this top shape, since we're only dealing with this part, it would be 2.25 minus 0.25. So we have 2.25 from here to here, divided by 2, which would give us the center. But then since we are basing it off of, this is where the axis is, we have to add this 0.25 back. So for this top shape, it ends up being, so it'd be 2.25 divided by 2, which is 1.125, and then plus 0.25. So plus 0.25 gives us 1.375. So 1.375. And these units, area obviously is in inches squared. This y bar is just in inches. And then since we're multiplying these two together, we'd be left with inches to the third for this term. So going back to the y bar for the long rectangle, it's just going to be half of your height in this case, because we know it acts right at the center. So it'd just be 0.25 divided by 2, which is 0.125 inches. So then for this rectangle 1, we just multiply these together to get this term. And if we go ahead and do that, it is 0.7734 inches to the third. And then for this one, we're left with 0.0703 inches to the third as well. So then, let's see. So the y bar, this y bar is when we were just looking at the individual shapes, right? So we need a y bar for the entire shape. And the equation to do that would be y bar is equal to the summation, there's that I again, of y bar times a, which we just calculated here, that's all these values are, divided by the summation of all the areas. So we already have everything we need calculated. We'll just do the summations down here. And so we get 0.5625 plus 0.5625 is equal to 1.125 inches squared. And then, so this would be the area summation, and this would be the y bar times area summation, which would get 0.8437 inches cubed. So then we have all the terms, now we just substitute them into this equation to get this location of the centroid for the entire shape that we have over there. So we'd be left with y bar equals summation of y bar times a, which is this term, so it'd just be 0.8437 inches cubed divided by this term that we calculated, 1.125 inches squared. And we see the units, these are going to go away, and we're going to be left with inches, which works out because that's the unit of like the centroid. So then after we do that, we get that the y bar, the total y bar for the entire shape, lies at 0.75 inches from where our axis is. So this symbol symbolizes the centroid. This line is that y value. So we know that from here to here, 0.75 inches. And that's the location of the centroid. So then, where that comes into play is in this equation right here, because this y sub p term, so this is when we're looking at a specific point on this shape. So these points we have are h and k. So this y term is the distance of those points in the y direction from this centroid line. So from here to here is what that yp term represents. So in this case, we would do 0.75, or we'd do 2.5 minus 0.75, which would be the distance between the centroid and point K. And to get to point H, well, we already have it. Point H lies on the axes, so it'd just be this distance. But since it's in terms of the centroid and we have to go down, then it's a negative 0.75 inches. And that's just how the sign convention works. So if you go below that centroid line, then it's going to be a negative term. So, all right, now this formula here, it's really the summation of these terms. So the way I broke it down was we have to do, so this term, remember, turns into this 1 over 12 BH cubed. So I broke it down, and since it's a summation of the shapes, it's 1 over 12 BH cubed for rectangle 1, plus the same term 1 over 12 BH cubed for rectangle 2, and then these just be plus the area times the distance squared for rectangle 1, plus the area times the distance squared for rectangle 2. So what these terms mean, this one specifically, this D, is the distance. So we calculated the centroid for the total shape, and we calculated centroids for the individual shapes. So all it is the distance from the actual centroid to these specified centroids for the different rectangles that we have. So what we do, since we know that y bar 1.375 would be above the actual centroid, we'd go 1.375 minus 0.75, and we get 0.625. So where can I make this? So then we know D1 is equal to 0.625 inches. And then D2, we do the same thing. We have 0.125 and 0.75. So we go 0.125 minus 0.75, and we're left with a negative 0.625. So equals negative 0.625. And that makes sense because the centroid for this rectangle is down here, which is below the actual centroid, so it'd be a negative distance value. So the areas we have calculated right here for both of them, they're equivalent, so we already know these values, and we can easily find these values. This is just the dimensions of the rectangles. So from there we can start plugging values in. So for rectangle 1, we know that the thickness is 0.25. So we have, so rectangle 1 sits on this axis, so it's the longer side is going to be the height in this case. So that because it's cubed and there's more material away from the centroid, that's the number that goes into the cube function. So for rectangle 1, it's going to be 1 over 12. The base is going to be the thickness, so it's going to be times 0.25 inches times the length of it, which is that 2.5 minus the thickness, so it'd be 2.25. 2.25 inches, and this term is cubed. So that's for rectangle 1. Moving to this term, it's plus 112. B, so in this case, the base is this term, where the height term is the thickness, because it's the other orientation. So then we have 112 times 0.25 inches cubed, and then times 2.25. So 2.25, because that's the distance. Okay, so that was for 2. So we got 2 terms down. And then this term we know is for rectangle 1, we have the area 0.5625. 0.5625. 0.5625 inches squared times d squared, so d1 squared, we calculated 0.625. 625 inches, and then this value is going to be squared. So I'll write that squared. And then, so that's that term, and we move on to our last term. We know it's the same area, so 0.5625, and then I'll run out of room times d2 squared, so it'd be negative 0.625. But it gets squared, so the negative goes away, but I'll write it. Inches squared. So then, we plug all that in the calculator. We are left with I of x, which is what we were solving for, right? Is equal to 0.4395 inches to the 4th. When we check our units, we know that the area moment of inertia is in distance to the 4th, and we know inch times inches to the 3rd, inches to the 4th. Same thing here, inches squared times inches squared, same thing, so it all checks out. So that's, now we have our I of x term, I sub x term, and let's see. I think that's everything. So then, if we take this equation that we started with, and we were given, so we're at this point, we are analyzing the internal bending moment. And so if we use point K, then we can write, so we're given a stress, we're solving for the moment. So we can rearrange that equation and solve for m. So we're left with m is equal to the stress at point K times the internal moment of inertia, or the area moment of inertia, whatever, divided by y sub p. And then this would be negative. So then we can just plug stuff in, because we have stress at K. We were given that 2600 psi. 2600 psi. I sub x, we calculated right there, times 0.4395 inches to the 4th. And then this y sub p term is the distance from this centroid line to the point. So in this case, we're analyzing at point K, so we need this distance, right? So it would be 2.5 minus 0.75 would give you that. It actually should be yk. So it should be the distance to point K from this line. So we're given, if we do 2.5 minus 0.75, we're given 1.75. So 1.75 inches. So then PSI, pounds per inches squared, if we think of it that way, then we see that these cancel out, and then this cancels with one of these, and you're left with pound inches, which is the units of a moment, right? So if we plug this into a calculator, we're left with the moment is equal to, and I calculated at negative 653.0 pound inches. So it's negative because the formula is negative, and this value, since we went above, I'm sorry. This value, since we went above that centroid line in the positive y direction, stays positive. So this is the moment for part A. Let's see that. So then, I'll go over here. So using this equation again, it's asking us to find the bending stress at point H. So for the first part, we were given the bending stress, and that's why we rearranged the equation to solve for the moment. But in this case, we solved for the moment since it's uniform throughout the shape. We can plug that in there. We can easily find y to h, and we know I have x already. So we just use that equation and plug it in. I'll write it in this corner. So it's the internal stress, and we're analyzing at point H, is equal to negative moment times the distance to that point divided by the area moment of inertia. So then we know it's equals negative moment, which is already negative. So negative 653 pound-inches times the distance from the centroid to point H, which since point H lies on our axis, the distance is just this distance, so it'd be 0.75. But since we went from the centroid down, so since we're below the centroid, that value is negative. So our y sub h term is a negative 0.75 inches. And then that I of x is just what we calculated over there to be 0.4395 inches to the fourth. So, since negative, 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 three negatives means it stays negative. So then we have equals, so this internal stress at H is equal to negative 1114.3 psi. So it's psi, we see inches, 2 inches in the numerator, 4 in the denominator. So these all go away. You're left with inches squared, pounds per inches squared, psi. And then that also equals like 1.1 ksi. So this is your answer for part B, and then this would be the answer for part A.